Hello everyone, this is Maggie Lei from Group 3. My other group members are Vara, Ben, Salome, and Neelish. For our research project, we have performed a systematic literature review of automated cloud security auditing solutions. Cloud computing has seen tremendous growth and continues to grow along with the development of mobile technology and the Internet of Things. This growth has been achieved through its benefits of lowering costs, convenience, pay on demand, and the ability to share computing resources. Cloud computing has not only become a critical part of the cyber infrastructure, but also a part of everyday life. The dynamic characteristics of the cloud is millions of users, data produced along with the applications and services provided for the users contributed to the expansion in the size of its attack surface. At the same time led to the increase in challenges on providing security for the cloud. To provide guidance on maintaining protection for cloud computing, there are various laws, regulations, policies, service agreements, as well as standards that have been put in place. Examples of cloud security standards include ISO 27002 or 27017, CCM, and NIST 800. In order to ensure the degree of protection is met for the various levels of service models offered by the cloud service providers, cloud security auditing comes in as a means of verifying compliance with the applicable laws, regulations, policies, and standards. In the past, many security auditing techniques have been proposed. However, many of them require manual efforts that are time-intensive or have considerable delay in response, both of which are not practical and error-prone. For cloud computing with its ever-changing nature, multi-tenancy, and its growth in size for its user base as well as the data associated with the users, an automated, continuous means of monitoring would be more ideal to increase the effectiveness, productivity, and accuracy of the auditing process. The automation of cloud security auditing would not only benefit cloud tenants and their users, but also the cloud service providers in increasing trust, transparency, and confidence in the underlying technology, as well as make it more convenient to generate any support documents for proofs. There is a lack of research done in surveying the different cloud security auditing methods, which provide high flexibility to users by offering efficient security to their data. In 2019, Kishore Babu and Gulu Parakash performed a systematic review of different kinds of methods involved in third-party cloud security auditing. These techniques are evaluated on the basis of effectiveness in privacy-preserving, overall performance, function, and security. Their paper gave an overview of cloud auditing and comparative performance analysis of different methods from the years 2014 to 2018. To establish an integrity check, the efficient privacy-preserving outsourced computation method is used to support multidimensional public data and efficiently outsourced to the cloud. Few more new crypto systems named as switchable homomorphic encryption with partially decryption, the identity-based data outsourcing, improved technique for order of preference by similarity to ideal solution, are tested on real-time systems and their security performance is analyzed in terms of completeness, soundness, unforgeability, correctness, authorized auditing, identity privacy, accountability, data traceability and recoverability, traceability and non-frameability. Majumdar et al. In their work published in 2019 addressed real-world issues in the cloud environment, explained the complexity of the cloud due to its virtual and physical layers, concentrating on the most challenging aspects of virtual layer 2 to layer 3 networks. They explained the need for cloud security auditing, the challenges in performing auditing such as high-level security properties, non-trivial log processing, reducing manual involvement, runtime policy enforcement, and practical response time. Also, the authors walk us through the existing solutions on cloud security auditing, which are categorized into retroactive, intercept and check, and proactive auditing. In summary, their work covered comprehensive knowledge on cloud security auditing, covering a wide range of security auditing issues and proposing new solutions to the challenges. Contrary to the aforementioned surveys, our work focuses on automated cloud auditing solutions proposed between the years 2017 to 2022. A systematic literature review is performed in this paper to investigate literatures published in this research area. We aim to gain insight on the state-of-the-art available solutions and to answer the following questions. Research question 1. What are the latest automated cloud security auditing solutions? Research question 2. What are their capabilities and limitations? Research question 3. What are future scope and research options? In order to understand our research better, here we are providing the background information on types of cloud security auditing approaches and mandatory steps within an automated cloud security auditing process. For the types of cloud security auditing approaches, there are retroactive approaches that are approaches that can catch violation of security policies after the fact by verifying cloud states mainly from logs and configuration files. The disadvantage of this type of approach is that it cannot prevent security breaches from happening, which can cause potentially irreversible damage. Intercept and check approaches are approaches that audit the impact of each change request to the cloud prior to approval or denial of the request. This type of approach may sometimes exhibit a significant delay in response. Proactive approaches are approaches that can verify possible user requests in advance by the use of assumption on the known sequence of user requests, the so-called change plan. However, assumption about fixed change plans might not be always realistic when it comes to the elastic and provision and deprovision actions of cloud tenants and users. In order to understand cloud security auditing and what is required for the automation of this process, Figure 1 on mandatory steps for an automated security auditing process is provided as a visual representation of what is involved. The mandatory steps for an automated security auditing process were first identified by Majumdar et al. And was also presented in a later extension of their study. In the first step, the auditing scope is defined. Within the auditing scope, the policy language, assets involved, and threats under consideration, the threat model, are identified. For each threat under consideration, a set of security assumptions are described. The second step is the collection of evidence associated with the audit. Most of the audit data usually appear in the form of events, logs, and configurations. Depending on the form of the data, the collection technique might vary. The third step is the processing of evidence collected in the previous step. The data must undergo sanitation, normalization to be categorized, and various techniques are used to represent the data for processing. During the second and third steps, how the data is stored is important since there may be a large amount of data generated over time due to the elastic nature of cloud computing. The fourth step is when auditing is actually performed to verify the process data against their respective policies for any anomalies, which will indicate whether any violations exist. In the last step, the audit output must be presented in a proper representation to ensure no sensitive information is leaked.
Hello everyone, so I will be covering the approach slide here, or approach slide deck. So for our approach to our personal research paper, we went for a systematic literature review. According to guidelines put forth by Barbara Kitchenham in a 2007 paper that developed the literature reviews of this type, this kind of review is designed foremost to be a formal way of discovering and analyzing literature to investigate specific research topics within a very broad domain. So a broad domain of technology, and in our case, that is a broad domain of cloud computing and cloud security. The steps in this review were developed and performed under those aforementioned guidelines, and some modifications and additions made later by other contributors. The inclusion of references from the relevant papers, known as snowballing, this project and paper will be using a snowballing process, has also been incorporated to identify additional sources in our chosen topic area. These steps included in the systematic literature review are as follows: formulation of a review protocol, conduction of the review itself, report of the review results, and the discussion of our findings. Our finalized review protocol will cover all the research questions, databases searched, the primary identification, evaluation, and data extraction of the actual content this is based off of, and our findings based on that. To reduce researcher bias, we had 2 authors develop the protocol, and then it was reviewed again by the other 3 authors and the rest of our group. After this review phase, discussion, iteration, and further group review molded the protocol into its finished state, which was subsequently used in our paper. So we went with 3 primary research questions that we wanted to answer to complete our survey. Rather simple, but this is an important step. The first is, what are the latest automated cloud security auditing solutions? What are the capabilities and limitations of these solutions? And what future scope and research options are available based on what is currently in the domain? So we obtained our primary studies used in the systematic literature review by searching databases that contain research in the domains of computer science and the domains of engineering, or computer engineering as well. We selected databases that contain conference proceedings or peer-reviewed journal articles, and databases that appeared in other systematic reviews on cloud computing topics. In the end, we selected 5 databases, these being IEEE Explore, ACM Digital Library, Elsevier, which is also known as Engineering Village, Springer, and Google Scholar. It is important to not let too many databases creep into these, as there can be great overlap and the scope can get unnecessarily and unmanageably large. To identify the search terms, we did follow a set of subsequent steps you can see on the slide. The first being extracting major terms from the research questions. Then the second, for each major term, generate a list of synonyms and alternative spellings for that term. Combine each major term with its synonyms or alternative spelling with the OR operator, and then link those major terms with the AND operator. So on the next slide, you'll see our resultant global search string that we used. So this is our very simple slide, is our resulting search string. So automated or automation, and cloud security or cloud protection, and auditing or monitoring or assurance. Really, this was what we decided in the end covered all the ground that we needed to with the search without getting too it. So this is our inclusion and exclusion criteria table. This depicts the criteria that we use to comb through our sources after the fact and sort of choose what to include and exclude. We went through the results list and evaluated each paper in turn. Everything that we used here is defined in Table 1 and was simply done to make sure we weren't using any irrelevant papers. Now, the 2 big steps that we took is we would use the title to exclude papers that aren't related to the research questions. That was an easy and obvious one. And you do the same with the abstract. Now, there are some more criteria in this table, such as we only could use English written papers, which makes sense, and we wanted our papers to be recent on the time scale here. Exclusions are pretty much the opposite of that. We wanted to make sure that this was automated cloud security because we wanted to be as granular as possible. So any solutions that don't have that are irrelevant. And any papers we couldn't get the full text of, other surveys, things like that were excluded as well. As for the distribution of our primary studies, you can see that they're a bit uneven, and that's to be expected with IEEE being as large and as useful as it is and us having access to that specific journal. But once all the relevant papers were identified with our search string, we used a snowballing process to search through the reference lists of papers and search for possible missing resources. The inclusion and exclusion criteria were applied again to those resources. Table 2 above lists the distribution of the primary studies from each database source. Note that the databases were searched in the order that they first appeared on the table. To mitigate duplication of sources in our count, any paper that was returned in the search by more than one database was counted only once, so we didn't have duplicates. Google Scholar was the primary database used in retrieving papers that we identified later in the snowballing process. And this star symbol that you'll see on Springer means that two of the research studies in this table, namely studies 9 and 10, RS9 and RS10, using our actual syntax, were published in the same book, and you'll see them referred to as RS9 and RS10 later in table 4. So these were in the same book, so that was important to highlight here. Each of these two studies were counted individually, and along with RS5, they make the 3 primary studies found in the Springer database. It's also worth noting that Research Study 9 was first published in the year 2016. However, because RS9 was republished again in 2019, we have decided to include it as a primary study. Its inclusion also helps give a better idea of how the work has evolved for the group of researchers. Since they were, first to propose these mandatory steps in an automated cloud auditing process, it's important to showcase that. Now we're moving on to the end of our approach here with highlighting how we extracted data. So this is our data extraction form. Well, this is the first half. It can't all fit on slides, but really the best way to showcase this, other than making a bunch of bullet points, is to show you the form itself. We have a name, we have the year published, we have the solution name, we have methods, cloud layer, scope, and evidence collection. We designed this form to record relevant data that was proposed in each solution or research paper to answer our 3 research questions. The data extraction form is presented in table 3 on our paper, and the design of this is influenced by the mandatory steps of the automated security auditing process. We concentrate on how each proposed solution handles the information involved in each step to gain a deeper analysis of what the advantages and disadvantages of the solutions are and see more detail into the techniques. We also want to find similarities so we can compare them and give a result on trends and general statistics of the field later. We aim to answer all of our, previously mentioned our 3 research questions with this as well. So we need to ensure that this covers that too. And we did. So we're on to the end here pretty much. This is simply, or the end of the approach pretty much. This is simply the second chunk of our data extraction form. Here we have things like performance metrics, limitations, and information if there's demonstrations of these technologies here. In many ways, this form follows the formatting of a paper in this field, and that's sort of something that I touched on earlier. It goes through the process in a way of security auditing. The fields describing what cloud technologies are used and what will be done for future work were essential in building our thoughts and analysis for other papers. Things like the platforms, figuring out what platforms have high development, and some more obscure platforms that don't. And one thing to note is the platforms we have listed here are simply examples. We do reference some other platforms that aren't here in the actual papers because the original papers that we took the information from were developed for slightly different cloud technologies. So we have evidence processing, auditing, output, and the auditing technique is specifically how violation is detected, so that's a very important one. The output is also important. It could be a report, it could be a dashboard, or it could need to plug into another technology. And limitations and future plan are something that we used ourselves to develop our recommended future plan. Once our approach was set, we executed the tasks that we had laid out and began our research. This takes us to the results, or the RQ1 research question 1 of our paper. This table, which is split between two slides because of its size, shows the results of this research question RQ1. And that question is, what are the latest automated cloud security solutions? This table shows the cutting edge solutions that have come out in the last 5 years, is what we defined as latest in this case, from the different journals that we designated. And I'll just briefly head over to the other slide after this so you can see the other papers. So again, this is just the latest papers in this area. You can see that we discovered 16 that fit our criteria. Yeah, and that's about it.
Hello everyone, my name is Nilesh. To answer the research question number 2, the capabilities and limitations of the solution presented in this paper, we have summarized this whole 16 research papers to give an idea of the capability of each of the solutions and its limitations. So let's get started with the research study 1, which is Cloud Trust, a security assessment model for the infrastructure as a service. This research study presents a cloud architecture reference model that incorporates a wide range of security controls and best practices. The cloud security assessment model is called as Cloud Trust, which basically establishes the high-level security matrices to quantify the degree of confidentiality and the integrity offered by the cloud service providers. The security status for a system depends on many factors, which includes security applications running on the system, the hypervisor, and the associated protection measures, and the design pattern, which basically used to isolate the control plane from the cloud tenants, and many others. This solution basically uses the unique attack path that covers the essential elements of the IaaS cloud architecture. It is basically based on the Bayesian network model. So we use basically various attack paths to kind of identify the to rate basically the IaaS architecture. So few of the attack ingress paths are the VM side channel attack, which is based on the VM vulnerabilities. The second one is the SDN virtual network, which basically uses the potential issues in any SDN. The third one is the VM attack through the hypervisor and others, which basically uses on top of the SDN attack. So when the hypervisor is compromised, the APT basically collects data from the host machine's RAM, any additional details such as the network architecture, credentials, keys, which can compromise the VMs, and many others. So the scope of the solution does not include the measures used in the external network enclaves, and also the possible next step for this solution is to use a full range of inside attacks and can perform on the platform as a service and the service software as a service CSPs. Now let's go to the research study 2, which is a mutual auditing framework for a service level security auditing in the cloud. This research study basically presents a mutual auditing framework in a cloud server model. So this interactive framework basically will keep track of different service modules from both ends. It will basically establish a mutual agreement of trust. The objective of this client server mutual auditing framework is to monitor the client activities and client applications from the server side, and also to observe server side activities and services by the client. Which basically kind of establish a mutual trust between client and the server. So in this model, basically client module monitors the server proficiency, the data traffic, and network intrusion, and the quality of the service rendered by the service provider. So the basic, it monitors the different service levels of the server and the clients, which includes the network performance, host level configurations, different auditing policies, and security measures. Um, so this is the key units that a server and client should include in its as its key unit. The server will have the operational infrastructure assembly, the advanced audit policy implementation, whereas and many others. And whereas the client will have the servers will monitor for the server configuration management, network configuration management, and few others. Now coming to the research study 3, which is basically a learning-based proactive security auditing. So this basically uses a proactive auditing approach, which basically starts the auditing ahead of the critical events, which has recently proposed as a proposal solution for delivering the practical response time. So this basically leverages a learning-based technique to extract the dependency models from the runtime events in order to facilitate the proactive security auditing of the cloud operation. This solution has been integrated to OpenStack, which is a very popular cloud platform, and it basically performs very extensive experiment in both simulated and the runtime environment. So this basically contains 4 modules: learning, pre-computing, likelihood, evaluator, and feedback. Now, this each presents the responsibility. Like the learning module is mainly responsible for conducting the learning of the probabilistic dependency model, whereas the likelihood evaluator is basically triggers the pre-computation based on the model. The pre-computing module basically prepares the ground for the runtime verification, and also so you can see here in this diagram this the flow overview of this approach, where you can see all the modules are interacting with each other, and at the end of the day the verification tool is used and the result is produced by the feedback module. Now let's coming back to research study 4, which is uh, used for the user level security auditing, which is RBAC, ABAC, or SSO. So this is a runtime security auditing framework for the cloud, which is mainly used includes the authentication mechanism or in the access controls. So this framework is also deployed on was deployed to test. It was deployed on OpenStack, which is basically like I said, it's very open, widely used open platform. So the main idea here is to reduce the response time to a practical level, so that to we can perform all the costly operations and during the initialization. So this solution basically contains 2 major phases. One is initialization phase, and second is the runtime phase. So you can see this is the diagram where the initialization phase and the runtime phase has been presented. During the initialization phase, the data collection, data processing is and the data is done, and at very offline verification is done during the initialization. So coming back to the research study 5, which is nothing but it's a security evaluation framework for the cloud security auditing. Uh, so this is basically security evaluation of the cloud service providers, where customer specified its security preferences, and then it kind of calculates the strength of cloud service providers security framework. So it has a few key factors. The key factor can consist of three components: security evaluation, security metrics, and the security index. There are few sub-factors. The sub-factors should be taken care by the security auditors. So they are responsible to kind of populate, update, and maintain the database so that it can reflect the appropriate security scores for the sub-factors. As a future goal for the solution is to develop the evaluation rules of the security matrices based on the fuzzy logic system. Um, this auditing factors basically contains these are the few security auditing factors like interoperability, transparency, malicious insider, the portability are taken care in this framework. Coming to the research study 6, which is based on the AWS, the security and the cost optimization. So this one basically is performed on the AWS to basically lower down the cost of the infrastructure used by a customer. So it basically introduces a requirement to design and main activity stream of the cloud system. So if you don't have proper knowledge of the AWS, you may lose money, and also it may lead to unfortunate consequences. The key function of this framework during the analysis and designs are register and log out, manage checklist item for security and cost optimization, scan the items. So these are few steps that are performed for this framework. And here is the component architecture of of the framework, where the user component controls the admin or the normal user. The app server is the main system which kind of process all the data. And MongoDB is used to store all the database, where web UI is here. Web app UI is the user interface that is accessed through any browser to view the data. Thank you.
Let's talk about the papers 7 to 12. Research paper 7 is deep learning based user level proactive security auditing for clouds. This paper presents a novel framework for proactive security auditing in clouds using the deep learning based techniques to improve the performance of security auditing. This paper automatically learns user behavior patterns from historical events based on LSTM and predicts potential violations at runtime. This framework has 5 modules. Data collection and processing module. In this module, collects unstructured data from the cloud and parses raw data into a structured format. Then it extracts the sequence out of event entries and prepares input data for the learning engine. The second module is event interception module, and this module intercepts each user events from the cloud management system at runtime and identifies the critical events that may potentially breach these properties. Third module is violation prediction module. This module learns probabilistic dependencies among events from sequence of events by leveraging LSTM and predicts critical events based on the probability dependencies and intercepted events. And the next module is compliance verification module. Once one of these critical events is about to occur, this module proactively verifies the parameters associated with this event and identifies the causes for considered security properties with storing the information results in the repository. And the final module is decision module, and this module provides decisions to the cloud according to the verification results and feedbacks to other modules by analyzing those results. This framework conducts 2 sets of experiments. The first set of experiments is to train and evaluate the predictive model, and the second set of experiments is to demonstrate the time efficiency of the deeps. Experimental results show that this approach keeps the response time to a proper level and improves the speed up significantly over existing approaches. The next paper we are going to talk about is multi-level proactive security auditing for clouds. The motivation of this paper is to automatically build a predictive model based on the dependency relationships between cloud events and proactively verify the security policies related to different levels of a cloud by leveraging this model, and finally enforce these policies on the cloud based on the verification results. This approach mainly performs two major steps, and their prediction and multi-level proactive verification. Prediction is to build a predictive model for cloud events. First, collect historic data from the cloud and then pre-process these logs to prepare them for a learning tools. Afterwards, capture the structure of the dependencies and also measure different parameters from the processed cloud logs, and finally obtain the predictive model based on these structures. And the next step is to pre-compute security auditing results. We first intercept cloud events, then predict future events from the currently requested event using the obtained predictive model from the previous step, and after that proactively conduct the verification process for these predicted events by utilizing the existing verification tools. So the experiments this paper conducted is the first set of experiment is to demonstrate the efficiency of the proposed multi-level proactive auditing. The second shows the response time. The results show the response time in several milliseconds in best cases and several hundreds of milliseconds in worst cases. The second set of experiment is to show the accuracy improvement by our proposed predictive model. After quantitative comparison between their predictive model and the dependency model proposed in leads, it shows the percentage of prediction match and prediction error for three different pairs of events. In all cases, our predictive model shows significant improvements. The prediction match rate is increased up to 2 times and the prediction error rate is up to 12 times. This proposed system ensures the best response time on average of 85.5% of the time. The next paper is auditing security compliance of the virtualized infrastructure. An automated framework that allows the auditing the cloud infrastructure from the structural point of view while focusing on the virtualization related security properties and consistency between multiple control layers. This framework has 5 main components: data collection and processing engine, compliance validation engine, audit report, and dashboard and audit repository database. To show the scalability and validity of their framework, we present our experimental results on assessing several properties related to auditing inter-layer consistency, virtual machines co-residence, and virtual resources isolation. This framework interacts mainly with the cloud management system, the cloud infrastructure system, and elements in the data center infrastructure to collect various types of audit data. It also interacts with the cloud tenant to obtain the tenant requirements and provide the tenant with the audit result. Audit data and security properties are formalized as constraint satisfaction problems, which is called CSP, and used a constraint solver named Sugar to validate the compliance. The Sugar is a CSP to SAT translated verification and validation tool. Researchers believe the approach shows scalability as it allows auditing a data set of 300,000 virtual ports, 24,000 subnets, and 100,000 VMs in less than 8 seconds. However, the collection of the data set took about 8 minutes for a cloud setup of 10,000 tenants, 100,000 VMs, and 300,000 ports. The next paper we'll be talking is auditing virtual networks isolation across cloud layers. This is a chapter in a book, and in this chapter they represented an automated offline auditing approach which focuses on verifying network isolation between tenants, virtual networks in OpenStack managed cloud at layer 2 and overlay. This framework consists of 4 main components: data collection engine, data processing engine, compliance verification engine, and dashboard and reporting engine. They measure scalability of their approach by measuring the response time of the verification task as well as the CPU and memory consumption for different sizes of cloud and in different scenarios. In the first set of experiments, they designed 2 configuration scenarios to study different response times in 2 possible cases: presence of violations and the absence of violations. In the second set of experiments, since Sugar supports several SAT solvers, they ran Sugar with different SAT solvers to investigate which option provides a best response time, particularly for property Experimental results show that CSV solvers can be used for offline auditing verification with acceptable response time and scalability in case of moderate size of data. Results also show that for properties handling larger data sets, we need to decompose the verification of properties over smaller chunks of data to improve the response time. The next paper is Runtime Security Policy Enforcement in Clouds. This is another chapter in the same book, and in this chapter, author explained the design and implementation of a middleware, namely Pheromone, to apply the proactive approach to OpenStack. Pheromone utilizes a previously developed proactive verification approach, LEAPS, also by the same researchers as its verification engine. Verification process consists of 4 steps. Each user request is passed through Pheromone on their paths to the internet service, and then Pheromone intercepts the request and extracts parameters which are predetermined according to the mechanism in leaps. Leaps verifies the extracted parameters, and then based on the verification results, Pheromone decides and enforces the corresponding action. If the results indicated the events can be allowed, Pheromone calls the next component in the pipeline and passes it to the intercepted arguments for further processing. If it is determined the event should be blocked, Pheromone stops the request by changing the argument value for the start response function to 403 forbidden, and an error message is returned to the user. In addition to security policy enforcement, Pheromone can also benefit log processing. Pheromone logs and examines the intercepted body of request in order to identify the type of log requested. This provides a feasible solution for more accurate log processing. The next paper we will be talking is the decentralized runtime monitoring approach, relying on the Ethereum blockchain infrastructure. In this paper, a decentralized customer-side monitoring approach to monitor and detect security service level agreement violations and autonomous compensate customers is proposed. This proposed approach monitors the compliance of cloud services to the contracted properties in security SLS. The approach relies on Ethereum blockchain as a decentralized platform to securely store monitoring logs and incorporate SecSLAs as smart contracts. The deployed smart contract integrate and aggregate measurable SLOs and check continuously the compliance of cloud services to contracted SLOs. Ethereum enables complex computations to be executed in the blockchain. Most important aspects of this blockchain are Ethereum accounts, Ethereum virtual machine, smart contracts, how to interact with the smart contracts. This paper uses 3 different SLOs in their evaluation and validation experiments to illustrate their proposed approach, namely percentage of uptime, percentage of proposed requests, and secure cookies forced. This approach is evaluated using 2 experiments. Experiment number 1. In the first experiment, we evaluate the functionality of the approach on Amazon EC2 by monitoring 3 EC2 instances, each in a different region, along with their web-based management interfaces. And the second experiment measures and compares the overall gas consumed by the Oracle. This paper analyzed the collected data to investigate the frequencies and duration of the outages during the measurement period. The shortest outage is the failure of a single request, that is an outage duration of less than 10 seconds. The longest outage duration extracted from the results of all instances is 255 seconds experienced in the US EC2 instance. A Python script is developed to calculate the total consumed gas by the security SLA compliance, validation, and compensation for 1 month. Raw logs and all the reports are depicted in a table. Then the rest of the papers will be explained by one of my teammates. Thank you.
Hello, I'm Vara Ari. I'll be talking about some of the research works, Research Study 13 to Research Study 16, done by different researchers in the area of cloud security auditing, and the findings of our team and what could be done going forward in this area to improve proactive cloud security auditing. A unified framework for cloud security transparency and audit sets out to propose a framework and a basic tool for security auditing. The authors designated their framework as Security Transparency and Audit Framework, STAF, and the tool used as Security Transparency and Audit Tool, also called STAT. This framework consists of a systematic auditing process for audit of cloud systems and analyzes information exposure. The tool STAT complements this by assisting in the collection of evidence based on predefined requirements and proposing corrective actions for fixing problematic areas and validating remediation. STAF was derived based on the following requirements: conceptualization of security transparency, specification of security transparency, collection of verifiable evidence, assessment of evidence, determination of CSP transparency worthiness. The objective of this framework is visibility for improved auditing. As for the STAT tool, auditor-controlled query response approach is utilized to help auditors move through the information needed to complete their job. Coming to the results of this research, the authors used user feedback to measure the acceptance and viability of their solution and received very positive results. The authors are confident that their tool will have a significant impact in the future security auditing of clouds. Proactive Security Auditing System for Clouds presented a proactive cloud security auditing framework named ProSAS that is also capable of intercept and check. ProSAS extended the learning-based approaches along with the combination of techniques used in the previous works of the same authors to improve its security property coverage, efficiency, accuracy, and automation. ProSAS consists of four major components: dashboard and reporting engine, interceptor, learning engine, and verification engine. The dashboard and reporting engine is implemented in PHP as web interface for user to place audit requests and view audit results. The interceptor is placed within the cloud as a middleware in between the cloud dashboard or command line interface and different services, which intercepts all tenant initiated events and forwards them to ProSAS. The learning engine first learns critical events using a formal verification tool on cloud configurations, then learns dependency models from the logs of different cloud services, and a Bayesian network and time series model, and finally initializes all other inputs of ProSAS. In the verification engine, the event manager contains caches for both actions and results. N-step evaluator measures for each critical event from the intercepted event using the current cloud context, and the proactive verifier queries the caches or watchlist databases to verify the parameters of the intercepted events. When a critical event occurs, ProSAS leverages and recycles those verification results to efficiently enforce the security policies. To address accuracy, ProSAS used a retroactive method for the learning of new critical events. The intercept and check aspect of the framework can respond in a few milliseconds with the help of a proactive approach. When it comes to the test results, the reported response times for this framework were 1450 nanoseconds at best and 8.5 milliseconds on average for a large-scale cloud with 10,000 tenants. ProSAS was able to learn more than 20 new critical events spanning 100 days, demonstrating an improvement in automation from previous studies. ProSAS is able to handle concurrent events by maintaining an event queue. However, the method of learning critical events in this approach still requires a manual inspection by a tenant admin or a security expert. Hence, complete automation is still lacking. ProSAS is less expensive than other general-purpose formal verification approaches. Single-step violation is also not yet efficiently handled by ProSAS. and also cannot resolve any conflicts or other issues in a policy description at this time. CSB Auditor, a cloud auditing solution specifically for storage broker systems. It was designed to secure the upper cloud layers by mitigation of human error. Much like other solutions explored in our paper, it collects evidence of unauthorized and unexpected actions, such as misconfigurations, unauthorized movements, copies, deletions that occur on a given system. It works in what could be described as a hybrid system of threat detection. While a rule engine exists as a component in the author's implementation, CSB Auditor really uses comparison of system states, expected state, and cloud state. It will go through what is referred to as a state transition when the system goes from an unexpected state to something else. Once in the state transition analysis, the system will compare states against one another to find potential signs of compromise or insecurity. This framework is fairly simple and easily plugs into report and alert generation. The writers used CVSS, which is Common Vulnerability Scoring System, for vulnerability scoring. Overall, CSB Auditor was said to be a good performer by the authors, detecting misconfigurations at a rate of over 98%. Based on this success, the authors continue to build upon their framework in their following studies with some new contributions. Continuous auditing and threat detection in multi-cloud infrastructure builds significantly on the previous work about CSB Auditor tool. And the objective here is to determine the viability of this tool for storage brokers. Using CloudRaid as their reference system, these authors translated the tool for this specific subgroup of clouds. In their new use case, the tool audits and protects the complete CloudRaid stack utilizing the same state transition analysis methods discussed in the author's previous work. Another notable contribution of this work is the author's approach to benchmarking. They validated the system by using a chaos engineering system called BrokerMonkey to measure the system response at a variety of fault levels. This BrokerMonkey system works by injecting faults into the system at varying degrees of intensity, and the authors analyzed how the system healed in response. Additionally, this implementation included the risk assessment feature of the author's previous works. The authors would like to move forward with a more integrated approach that extends to security event aggregation and analytics. This brings us to the last slide of our presentation, where our team tries to answer the research question number 3 of findings and future scope. It is observed that the auditing approaches in RS3, 4, 9, 10, and 11 are signature-based and therefore cannot detect any zero-day security violations. These approaches also cannot prevent potential privacy concerns from the audit results. The efficiency of the current runtime approaches in RS3, RS4, RS11 may be affected when multiple user requests appear simultaneously. The current proactive solutions, RS3, 8, 11, 14, cannot efficiently handle single-step violations. Among the 16 primary studies, RS3, 7, 8, 14 are machine-learned based approaches, whereas RS12 is the only approach that leverages the blockchain infrastructure. Based on our findings, we suggest that anomaly-based or hybrid, i.e. the combination of signature-based and anomaly-based auditing approach may be used to improve the coverage of the proposed solutions in RS3, 4, 9, 10, 11. A parallel or distributed approach might increase efficiency of the runtime approaches. There should be a more uniform way of defining security standards for the CSPs to follow in providing the required data for cloud security auditing to make it easier for the researchers to model and formalize the security properties to be implemented in future frameworks. Even one of the latest studies published in 2021 in RS Research Study 14 was unable to resolve any conflicts or other issues in a policy description. Only 3 out of 16 studies, making only 18.75% of the identified studies, were able to resolve conflicts or recover cloud states by utilization of restoration of expected state. Overall, we have found that automated solutions for cloud security auditing is still at its infancy, and there is no single solution available to verify multiple layers of the cloud. Hence, more research should be performed to address the aforementioned findings. Thank you for your attention. This brings us to the end of our presentation.